Next important concept that we are going to talk about is the GPU architecture. See, till now I have told you that GPU is a hardware which is present internally in your either in your internally on your processor chip or externally, which is capable of implementing the concept of parallel computing environment. So, and this is GPUs are mainly used for dealing with the larger sets of data, or for especially for gaming applications we implement the concept of GPUs. But what is GPU? How does it look like? What is the architecture of GPU? So, if you see GPU stands for graphics processing unit. So, it refers to a chip or an electronic circuit which is capable of rendering graphics for a display on an electronic device. So, it implements the concept of parallel processing where multiple processors handle separate parts of the same task. So, a GPU contains multiple cores where each cores run at a clock speed. So, the example, there are different types of GPUs from different companies available, Intel GPU, NVIDIA GPU. So, there are different companies, they have manufactured their own GPUs, and we are here considering an GPU which is manufactured by NVIDIA GPU. So, NVIDIA is nothing but it is a GPU which is designed by NVIDIA Corporation, which is an American multinational technology company which is based at California, and it is a software company which designs the graphic processing units or your GPUs as well as APIs, application programming interfaces, and high performance computing, and this is done by NVIDIA GPUs. These are designed by NVIDIA Corporation in California. And we are going to focus on NVIDIA GPUs. If we see NVIDIA G4 GTX 280 GPU, it contains internally 240 cores present internally in its hardware, each of which is within a core it is heavily multi-threaded, and it implements a concept of single instruction multiple data stream. So, the Flink's taxonomy, the single instruction multiple data stream is implemented where the single instruction is going to run on multiple sets of data. So, it has internally 240 cores. Core is nothing but a functional unit or ALUs present internally in your hardware. So, if you have 240 cores, it is capable of executing performing computations at 240 at a time. So, and moreover, as I told you, GPU is not a standalone device, it cannot work on its own. So, there are combined with the CPUs. So, along with the CPU, you need to have a GPU attached to it in order to implement the concept of parallel processing environment. And the CPU is responsible for initiating the computation on the GPU and transferring the data to and from the GPU. So, whenever there is a parallel task that need to be done by as a part of the program, the CPU has to identify that parallel task and it has to assign that task to the GPU. And whatever data that is required to perform the task by the GPU has to be shared for the has to be transferred from the CPU to the GPU. So, if you take a GPU architecture, it mainly so this is an architecture of a modern GPU which contains a device memory, registers and shared memory. So, you have multi-processors where each processor has multiple cores internally present in it. So, if you see the composition of a GPU, it mainly contains different parts such as a compute device, GPU RAM, workload distributor, compute units and processing elements. So, this is so here you will understand it better here. So, this is an architecture of a modern GPU. If you see, it contains this is your multi-processors, this is one multiprocessor, this is one multiprocessor. So, like that you will have multiple processors present inside your GPU. The GPU and each and every multiprocessor has its own local memory or a shared memory along with a RAM. This is a data cache or a RAM that is pertaining to that particular GPU. Apart from this, we have a global memory and a constant memories, and these are specific that acts as the intermediate between the CPU and the GPU. If at all a CPU wants to transfer any information, want to share any information with the GPU, it will share it by placing it to the global memory and constant memory. So, here each and every multiprocessor internally it has multiple compute units available where each compute unit is capable of processing multiple instructions. So, if you see here multiprocessors, we have multiple cores, and each multiprocessor has its own set of registers and a shared memory, and overall if you consider this entire thing is a GPU, it has one global memory which is called as a device memory. So, here GPU technically we call it as a device, CPU we call it as a host. Host means the CPU, device means GPU. So, this is called as a device memory, which is a shared memory which is shared among multiple processors or multiple multiprocessors which are present in the GPU. So, this is a multiprocessor. So, this is the example block diagram of a GPU system of which contains two compute devices. So, here we have two multiprocessors. If you consider these two as two multiprocessors, each and every multiprocessor internally, this is one multiprocessor which contains multiple compute units or a functional units present in it, and it also have a GPU RAM and as well as a workload distributor. And this is one compute unit which is nothing but this one. This is one compute unit. So, here you have one more compute device which has multiple compute units present, and this device has a workload distributor and the GPU RAM, and each compute unit is capable of executing one instruction, and the workload distributor of a GPU is responsible for distributing the work among multiple compute units of the particular compute device. And this is a host. Host is nothing but a CPU. So, the CPU will communicate with the GPUs. Here we have two GPUs. So, the host will communicate with the GPUs by transferring the information to and from the CPU and the GPU. So, this is the internal diagram of a compute unit. If you take this as a compute unit, this is the internal diagram of each compute unit. So, each and every compute unit internally have multiple cores present in it. So, these are multiple cores present in each compute unit, and this compute unit has its own private memory, a local memory and a thread scheduler. So, private memory is nothing but the memory which is private only to this particular core, and the local memory is nothing but it is local to that particular device, and the thread scheduler is responsible for, core is nothing but a thread here, is responsible for scheduling the scheduling the task between the threads. Next, the types of memories in GPU. As we have already seen the diagram, so GPU apart from its own dynamic RAM that is present, it has different types of memories that are available, because the dynamic RAM which is available in the device or a GPU, it is very slow and expensive. So, in order to overcome this problem, there are different other types of memories that are available in the GPU. So, we will see them. So, the types of memories are per thread local memory, per block shared memory, per grid global memory and read only per grid constant. So, this is about the compute unit. Next, we are going to see about this GPU hardware versus software. So, there are some technical terms in terms of a hardware and software. If you see the hardware view, the entire GPU device, we call it as a GPU device, but in terms of a software, when you refer it in terms of a programming side, we call it as a kernel. Next, coming to the multiprocessors. So, we have multiple processors present in a GPU device. So, here we call it as a multiprocessor. Here that is called as a block. So, then in terms of your memory, multiprocessor memory, each and every memory pertaining to the multiprocessor, we call it as a multiprocessor memory. Here we call it as a block specific memory. We call this as a block. So, we call it as a block specific memory. Next, coming to the cores which are present internally in a multiprocessors, we call it as a cores. Here we refer them as a threads. Next, coming to the memory GPU, if you consider this as an entire GPU device, and this is a memory which we call it as a GPU memory, and in terms of a software, we call it, since we call this as a device, so this entire GPU is called as a device or a kernel, where we call this memory as a device memory. So, in terms of a software, we call them as a kernel, thread, block specific memory and device. But when you refer it in terms of a hardware, this device is called as a GPU device, we call them as a cores, we call this as a multiprocessor, and this is called as a multiprocessor memory, and we call it as a GPU memory. And the CPU, we call it as a CPU memory. And in terms of a CPU memory in software, we call it as a host memory. CPU is called as a host, whereas GPU is called as a device. So, In terms of software, device is a kernel, core is a thread, the multiprocessor is a block. The specific this memory specific to a multiprocessor is a block specific memory, where the memory specific to a device is called as a device memory. Next, we are going to talk about different types of memories in the GPU. So, the GPU has its own dynamic memory. So, apart from the dynamic memory, we have other different types of memories available in the GPU, because the GPU, the dynamic memory that is available in a GPU is very slow, and moreover it is very expensive. So, in order to overcome this problem, we come up with a different other types of memories that are also existing in the GPU device. So, the types of memories that are present in the GPU are per thread local memory. So, now we have an idea of what is a grid, what is a block, what is a thread in terms of software. So, per grid global memory, per block shared memory, per thread local memory, and read only memory, per grid constant memory, which is a read only memory. So, this is a GPU device which where we have different types of memories here. So, if you consider this as a GPU device still here, this is a memory pertaining to the GPU device. We call it as a data cache or RAM of that particular DRAM of the particular GPU device. So, you have multiple compute units that are available in the GPU, and each and every compute unit has its own local memory or the shared memory, and this particular shared memory is shared among multiple processing elements which are present in the compute unit. And if you see here, these two compute units has its own local memory or a shared memory which is shared by them, and this compute unit has its own local or shared memory which is shared by those two these processing elements. So, and if you take each and every processing elements, it has its own private memory. So, for each and every processing element, a private memory is stored to store its private data, and whatever data that is common to the entire compute unit, that is stored in the local memory or a global memory. And we will talk about each one. The first is a global memory. So, here we have other two types of memories called global memory and constant memory, and these types of memories are used for communication between the CPU or a host as well as a GPU. So, these are used for communication between the CPU or a host as well as a GPU. Whenever the CPU wants to transfer the information or share an information with the GPU device, then it places that particular information into the global memory and the constant memory. And similarly, whenever GPU gets an output that has to be shared back to the CPU, then it is going to place it into global memory and transferred to the CPU. So, here there are two types of memory, global memory. So, the global memory is nothing but a high latency memory, and there is no limitation of what threads will access the global memory. So, all the compute unit will have multiple processing elements, and all the processing elements of all the compute unit present in the GPU can have an access to the global memory. The global data that is common, if you have a program, the particular program is shared among multiple compute units, and there is a global data that is required for all the compute units. That type of data or information is stored in the global memory, so that all the compute units, all the processing elements of the compute unit can have equal access to the global memory in order to access the data that is required. Next type of memory is a constant memory. So, the constant memory is nothing but that is also used for a communication between the CPU and the GPU or the host and the device. So, here the main use of a constant memory is it is a read only memory. So, you cannot perform any writing or updation into the constant memory. And why do we require a constant memory is, for example, say I want to calculate the area of a triangle which is say pi r square. So, here pi is a constant. So, that is constant throughout the execution of the program. So, the particular with a multiple sets of data, I want to calculate the area of a triangle pi r square, where I require the value of pi, which is 3.14. That type of information or the constant values are stored in the constant memory and being accessed by all the processing elements of the compute units. So, the constant variables which are required throughout the execution of a program are stored in a constant memory. Once you write the data into the constant memory, that is used only for a reading purpose, you cannot update the data in the constant memory. So, the next type of memory, so if you see here, this is a global memory and constant memory that are used for communication between your host and the device. And then you have a block is nothing but a compute unit in terms of software, where each and every block has multiple threads present in it, where so within a block you have a shared memory, so that multiple threads of a block can access the shared memory, and registers. So intercommunication between the threads of a block can be done by means of a shared memory. And the registers, each and every thread has its own local private memory, which is called as a registers. So we call it as a per block shared memory, per thread private memory, which is called as a register, and global memory and constant memory, which are used for communication. It is per thread, we can call it as a per grid global memory, per grid constant memory. For the entire grid you have one global memory and one constant memory. So global memory, there is one more thing that we have to take. So it is used for communication between the host and device. So the contents which are stored in a global memory is visible by all the threads which are present in the particular grid. So if you consider this as a grid, all the threads of the particular blocks which reside in the grid can have an access to the global data which is present in the global memory. Next, whenever the CPU wants to share an information with the GPU, it has to allocate some space into the global memory, some space. So it allocates some space into the global memory first, and then the information from the host will be transferred to the global memory, so that the grid or the device can access that particular information. And once the computation is done, entire data is being used from the global memory. If the GPU no longer requires the data which is present in the global memory, it has to free the allocated space of the global memory. And we require two types of functions here called CUDA malloc and CUDA free. So the CUDA malloc function is nothing but whenever a host want to store a data into the global memory, it will allocate some space in the global memory, and that is done by means of a CUDA malloc function. So it allocates an object in the device global memory. So this function mainly requires two parameters. The first one is the address to the pointer, which points to the memory space where the particular space has been allocated, and how much bytes. Like for example, say I want a 4 byte space in the CPU wants 4 byte space in the global memory to store some data. So if the first parameter points to the address to the pointer, the second parameter points to the size of an allocated object. It's like how much space, 4 bytes. So that is specified by the second parameter. So once all the threads of the particular block have an access to the global data which is present in the global memory, and when it is no longer required, it is also the responsibility of the device to free the memory space which has been allocated. So in that case, that is done by means of a CUDA free function. So it frees the object from the device global memory. So this is an example, CUDA malloc. So pointer MD represents to the pointer to the object to the address where the particular space is allocated in the global memory, and size represents the size of the space which is allocated. And to free the space, CUDA free of the pointer, whatever pointer we are defining here, it has to be defined so that the particular space will be deallocated. So we have already seen what is a constant memory, what is a global memory, what is a shared memory. So this diagram we have already seen the types of memories. Next we are going to talk about GPU computing. So GPU computing is a use of a graphic processing units or GPUs as a co-processor. Along with the CPU, we are going to make use of a GPUs in order to accelerate the CPU for mainly for high-end applications such as scientific applications and engineering computing. We implement the concept of GPU computing. And GPU computing applications accelerate the applications which are running on the CPUs by offloading some of the compute intensive and time consuming, whatever is there in the application, whatever is the time consuming portion which requires the parallel computations that are being executed on the CPU, on the GPUs, where the rest of the application will still run on the CPU. So the applications runs faster because it is using the massive parallel processing power of GPUs to boost the performance. So how the communication will take place between the CPU and GPU? So this is your CPU which has its own memory, and this is the GPU which has its own dynamic RAM, and whenever, as I told you, whenever a program, we need to say, for example, I want to execute a program, the data pertaining to the program resides in the CPU memory. and whenever the parallel part of the program has to be run on a GPU, it is the responsibility of a CPU to store the data into the GPU, to allocate some memory space in the global memory of the GPU and share the data into the global memory, so that the computations will be done on the GPU. So, that is done using 3 steps communication. The first step is copying the input data from the CPU memory to the GPU memory. So, whenever we have a task that need to be done as a part of a program on a GPU, we need to run it on a GPU, we need to share the data which is required for running the particular task. In that case, the data will be copied from the CPU memory to the GPU memory. This is the first thing. The second thing is we are going to load the particular program and execute it by taking the data from the DRAM which is available in the GPU, and once the output is available, that output will be placed into the DRAM of the particular device and it will be transferred to the CPU. So, the last thing is we are copying the results from the GPU memory to the CPU memory whenever our results are available in the particular memory of the particular GPU. So, this is how the communication, they may ask you to explain how the communication between the CPU and GPU takes place. It takes place mainly using these 3 steps: copying the input data from CPU memory to the GPU memory, and next we are going to load the GPU program and execute it, and once the execution is done, once the result is available, then we need to copy the results from the GPU memory back to the CPU memory, so that they will be displayed back to the user. Next, the last thing we are going to talk about the parallel programming languages and models. So, we are talking about different types, we are talking that parallel programming can be achieved or parallel processing can be achieved by using the concept of parallel computing or a high performance computing. So, what are the languages which are supported in terms of parallel programming? So, they are called as the parallel programming languages. These languages are designed to program the algorithms and applications on a parallel computers, and the well known parallel programming languages are OpenCL, Open Computing Language, CUDA, Compute Unified Device Architecture, as well as OpenAMP, Open Asymmetric Multiprocessors, and HIP. So, these are the programming languages which specifically provides the parallel programming, and you can write your code to implement the parallelism among your application using these languages such as OpenCL, CUDA, OpenAMP, and HIP. Out of them, OpenCL and CUDA are the well known programming languages which are designed for parallel computing, and CUDA is a parallel computing platform which is developed by NVIDIA Corporation. It allows the developer to work with a GPU accelerated code. So, here you can write a code using C++, Python, and Fortran languages that supports the parallel programming environment in terms of CUDA, and it is widely used in scientific computing applications as well as the machine learning applications. Then OpenCL is a cross-platform open standard for parallel programming, and it allows the developers to write the code in C++, Python, and Java, and it is supported by a wide range of hardware. There are different types of GPU hardwares available, as I told you, AMD, Intel, NVIDIA, they have their own GPUs. So, this particular OpenCL is supported in all the different types of hardwares manufactured by AMD, Intel, and NVIDIA corporations. So, next the thing we are going to talk about parallel programming models. So, what are the different types of parallel programming models that are available which implements the concept of parallel programming? Shared memory model, message passing model, thread model, and data parallel model. So, we will see each one in detail. Shared memory model. In case of a shared memory model, we have multiple processors which are distributed, which are present in the system, and we have a shared region of memory, we call it as shared memory, and whatever the data that are required by the multiprocessors which is present in the shared memory, which is shared among all the processors which are connected in the system, and they are going to work on the data by accessing the data from the shared memory. So, that is called as a shared memory model. Coming to the advantages of a shared memory model, since we are having a centralized system where your information is kept into a memory which is shared, which is a centralized memory which is shared by multiple processors, the program development becomes simple, and there is no need to explicitly specify the communication between the data and the processors. They can easily, whichever process wants to access the data, it can access it in the shared region which is available among all the processors. And coming to the disadvantages, the users, since it is not private in their own local memory, it is not processors does not have it in their own local memory, they cannot understand where his variables are being stored. They can be stored at any part of a shared memory, any region of a shared memory. So, that is a major disadvantage of shared memory model. Next, we will come across the second type of a model, which is called as a message passing model. So, in case of a message passing model, you have multiple processors which are connected in a system, which are connected by means of a network, and you have different types of multiprocessing interfaces. So, MPIs are nothing but multiprocessing interfaces, and here you have your data distributed throughout the network among multiple processors. You will not have a shared region where entire data is stored at a centralized location. Your information is stored among multiple CPUs which are connected in the system. You can have the data present anywhere. So, for example, say this particular processor needs a certain amount of data which is not available in its memory. Then it can access the other processors, it can get a request, it can request the other processor for that particular access of the data. And here in case of multiprocessor interfaces, we have the concept of two functions called send and receive. So, whenever a processor requests any information which is present on other device, it can request the information by making use of a send function. So, for each and every send function, we require a receive function, so that the corresponding device which has the data present in it, it has to respond to the request of the particular device by using a receive function. So, the communication between the multiple processors for accessing the data takes place by means of send and receive primitives. And coming to the advantages of message passing model, the data can be stored anywhere, and the communication between the processors is very simple, which can be defined using interfaces which are present, and there are many message passing interfaces that are available. So, these are MPIs are nothing but message passing interfaces. So, there are different types of message passing interfaces available that allows the multiple processors to communicate with each other in order to access the data which is distributed across the network. Next, coming to the disadvantages, the programmer should take care that there is a receive function. For every send function, we need to have a receive function. So, if there is no response from the receiver's end, then the other process which is requesting for the data has to sit idle. So, if any of the process does not respond, if it is quiet, other also will stop working, they are dependent, because the sending process is dependent on the receiving process for the data that need to be executed on the sending machine. Next, the third type of a model is a thread model. So, here we have a single threaded processes and multi-threaded process. So, in case of a single, you can execute the multiple tasks. So, different threads can be executed on a same machine or on a different machine. As we know, thread is nothing but a unit of execution. So, multiple instructions can be executed on multiple threads at the same time, and the threads can reside on either the same processor or they can reside on a different processor. If the threads are executed on a same processor, then the processor switches between the threads in a random fashion. The CPU or the processor switches among different threads in a random fashion, and if threads are executed among different processors that are existing in the system, they are executed simultaneously. So, these threads which are present internally, they communicate by means of a global memory. And coming to the advantages, the programmer need not has to worry about the parallel processing. And disadvantages, inter-thread, we have to take care that no two threads update the shared resources and simultaneously. For example, since they have a shared memory, they access the data through a global memory which is shared among multiple threads. For example, when one thread is performing a write operation, at the same time the other thread cannot perform a read operation. So, there should be synchronization that has to be maintained between multiple threads that are existing in the system. The last type of a model is a data parallel model. So, data parallel model is nothing but it implements the concept of Link's taxonomy, which is single instruction multiple data stream. So, here this is an example of a data parallel model. For example, for a single instruction, you are executing a single instruction on multiple processors on different sets of data. That is generally about a data parallel model. So, if you see here, we have a single instruction, we have two arrays here, xi and yi. So, we are going to calculate zi, which is nothing but xi plus yi, and we are having a loop here for I is equal to 0, I less than 100, I plus plus. So, this particular instruction is stored, the information which is required to execute this particular instruction is stored in the global data or a global memory, and all the processors have an access to the global memory, and they are going to work out on the same instruction on different sets of data. If you see the processor 1, it is executing on I is equal to 0 to 25, whereas processor 2 is executing on 25 to 50, 50 to 75 and 75 to 100. So, the single instruction is being executed on different sets of data. So, we call it as a data parallel model, which is nothing but, according to the Flynn's taxonomy, we call it as a single instruction multiple data. So, this is about different types of parallel programming models. Thank you.